Imagine you're building a house. You could slap some walls together, toss on a roof, and call it a day. Sure, it might stand for a while, but what happens when a storm hits? That's where the solid principles come in. They're like the architectural blueprint for your code, ensuring it's not just sturdy, but resilient. Think about it. Would you rather have a house built on a shaky foundation, ready to collapse at the slightest breeze, or one with a solid base capable of weathering any storm? The same goes for your code. So in this video, we will be learning about solid principles which will help you do that. Sure, following the 5 solid principles might take a bit more time and effort upfront, but in the end, you'll have a code base that's flexible, adaptable, and built to last for your grandchildren to see. So whether you're constructing a skyscraper or creating your own application, remember, strong foundations lead to stronger structures. With that understood, let's get into the video and learn about the S in solid principle, which stands for single responsibility. So the single responsibility principle states that a class should only have one reason to change. Although this definition seems simple at first, it can be confusing when you apply this in your own software. That's because a reason to change can be different for different people. Let's say I have code like this. We have a class of user manager with 2 methods in it, authenticate user and update user profile. In authenticate user, I'm just returning true, simulating the success of authenticating the user. In update user profile, I'm printing that user profile was updated for a particular username. You might think that this is a nice little class and everything's alright with it. However, this is a violation of the single responsibility principle. Why? This class combines authentication and user profile management logic, and they can be considered different responsibilities because they might change for different reasons. For example, authentication logic might change because there's some update in security or changes in authentication protocol. Profile management logic, on the other hand, might change due to update in the user profile structure or the way the data is stored. Since the user manager class is changing for 2 different reasons, this is a violation of single responsibility principle. So how can you make sure that this code follows single responsibility principle? To do that, we'll have to create 2 different classes. One class for auth manager and another class for profile manager. So this auth manager is going to contain all the auth related logic, which I can put over here. And this profile manager class that I have can contain this function. It will contain all the profile management related logic. And this way, we have a code that follows single responsibility principle. Auth manager will only change if some authentication related tasks change. And profile manager class will only change if some profile management related tasks change. Now you might think, how do I go about making the decision that the class follows single responsibility principle or not? And the fact is, it can be difficult. A key thing to remember at this point is that it is people who request changes, and you don't want to confuse those people or yourself by mixing together the code that many different people care about for different reasons. If you keep this thought in mind, you'll be able to make any decision related to single responsibility principle. If it helps, there's another wording for single responsibility principle. It is that we want to gather together the things that change for the same reasons, and we want to separate those things that change for different reasons. So what are the benefits of single responsibility principle? Single responsibility principle makes your code easier to understand. So by having single responsibility for each component, you're able to name your components more clearly and consistently, which improves readability and communication. So in our example, instead of having a class called user manager that handles authentication, authorization, logging, and profile management, we have separate classes for each of these concerns. So we have auth manager and profile manager. If we want, we can create another class called logger that will log stuff out. These classes are more likely to be reusable in different contexts as they're designed to perform a specific, well-defined task. Single responsibility principle also helps ease maintainability. That means changes related to one responsibility do not affect the others. For example, if I make some changes in this code, it might affect other methods too. However, If I make changes in Auth Manager, I know authentication related tasks is being changed. Code following single responsibility principle is also often easier to test. Unit tests can be more focused on the specific functionality without having to account for unrelated concerns. In User Manager, we would have to be concerned about all of the methods, but in Auth Manager, we know everything is auth related, and Profile Manager, everything is profile related. So now that we've understood single responsibility principle, let's go to the O in solid principle, which is open or closed principle. Open or closed principle states that software entities, that is classes, modules, functions, etc., should be open for extension but closed for modification. That seems contradictory, doesn't it? How can something be open for extension, meaning we are able to add new features, but closed for modification? It basically means that you or your team members should be able to add new functionalities to an existing software system without changing the existing code. Let's take an analogy to understand this. Imagine you're building a house and suddenly you need to add an extra floor. The open or closed principle is like having a design that allows you to add those extra floors without knocking down walls or rerouting the plumbing. Your house should be open for extension but closed for modification, which means you can add new functionality without messing with the existing features in your house. You want that. You want your house to be expandable without being a nightmare to renovate the entire thing. Let's understand this with a code. Let's say we have code like this. We have a class shape which takes a property type. This type is a string which can be circle, rectangle, square, or any other shape. Then we have a class of area calculator with a method inside of it called calculate area. It takes in a shape and then checks. If the shape's type is circle, then we want to return 3.14 into 3.14. Otherwise, we'll check if it is a rectangle. If it is a rectangle, we'll be returning 4 into 5. If it's none of them, we're just going to return 0. In this example, the area calculator violates the open or closed principle because every time a new shape is introduced, it requires modifying this existing area calculator class. And that approach is not scalable and it can lead to maintenance nightmare. What I'm talking about is if I try to use else if shape.type is equal to square. And then if it is a square, I want to return 4 into 4. So I had to modify this area calculator class to add another shape. If I have to keep doing it, we are not following open closed principle. As I said, it should be open for extension but closed for modification. So how can I make sure that another shape can be added without changing this area calculator class? And to do that, I'm just going to comment this code and write code that follows OCP or open closed principle. The first thing I'll be needing is an interface called shape. So to create an interface in Dart, we can just do abstract interface class shape. We're not using abstract class shape. We're using abstract interface class shape because we need a true interface. Now, what is the difference between abstract classes and interfaces? Abstract classes are used to provide a base class for concrete subclasses to inherit from, while interfaces are used to define a set of methods that a class must implement. So we want an interface here that will force every shape that we create to have a particular method, and that method is calculate area. So every class that implements the shape interface should have this calculate area method, and that's what I'm going for. The first shape that I'm going to add is circle. So I'm going to have class circle and that is going to implement shape. Once I do that, I will have to add calculate area method inside of this. So let's add it at the rate override double calculate area. And then we can return 3.14 into 3.14. And if we want to go one step further, we can actually take the radius from the constructor of this class. So we can have circle this dot radius, and then we can do 3.14 into radius. There we go. Now let's create another class, and that is going to be a rectangle class, and it's going to be very similar to circle. So I'm just going to copy paste this. So this will be called rectangle and it's going to implement shape as well. Now instead of asking for radius, we're going to ask for length as well as the breadth. And also we'll change rectangle constructor. And now instead of doing this, we will calculate the area. So what we have done till now is created an interface and two classes that implement that interface. Now all I need to do is create this area calculator class. So I'll do it this way, class area calculator. And inside of that, as usual, we are going to create our method calculate area. And it's again going to ask for the shape class. But earlier we were asking for a normal class shape, and this time we are asking for the interface shape. And what I'm going to do inside of this method is very simple, return shape.calculateArea, because the shape interface has a calculate area method created inside of it. So this entire code now follows open or closed principle. It does a very similar thing to this. You pass in the shape, and based on whether it's circle, rectangle or square, it's going to return some value. However, the main difference is this code follows open or closed principle. And that's because if I want to add another shape to this, I don't have to modify this area calculator class. What I can do is outside of this class, I can create another class called, let's say, square. And that implements shape. And again, I'll only have to ask for the side in square. And then I can modify my calculate area function to return side into side. Nothing is being changed in area calculator. However, I've added a new feature. So this area calculator is closed for modification, but yes, our entire code was open for extension. We added a new feature that allows us to calculate the area of square. Earlier, we had to change this method to do so. However, it's not required now. The benefits of using open-close principle is that OCP really allows systems to be easily extended with new functionality without modifying existing code. So this promotes the scalability of the system as new requirements can be accommodated through extension rather than modification. And by preventing changes to existing code over here, OCP reduces the risk of introducing bugs or unintended side effects. OCP also promotes design patterns. OCP is a foundational principle in many design patterns such as strategy, decorator, and factory design patterns. So if you embrace OCP, you embrace design patterns. Another benefit of OCP is that it encourages abstraction. So following OCP will often lead to the creation of these interfaces. And interfaces are like contracts for the classes that are going to implement it. So interface is going to define how the class is going to look like. And this encourages abstraction and helps in defining clear boundaries between different parts of the system. So now that we've understood OCP, open or closed principle, let's get to the L in solid principle, which is list cost substitution. List cost substitution has more of a mathematical statement. It states that let phi of x be a property provable about objects x of type t. Then phi of y should be true for objects y of type S, where S is a subtype of T. Now what does this even mean? It means that objects of a superclass should be replaceable with objects of its subclasses without affecting the correctness of the program. So let's say I had code like this. We had an abstract class animal with one method designed inside of it, make sound. And then we had a class lion which inherited from this animal abstract class. And then it printed roar inside of the make sound function. Then we had a global function make animal sound which takes in an animal and just returns animal.make sound. Then in the main function, I've created a variable called animal which is equal to lion. And here I've said that the type of animal is the animal abstract class. And then we have said make animal sound and passed animal to it. Now, if I try to run this, it is going to print out roar once. Now, what does list cost substitution mean? List cost substitution means that if lion is a subtype of animal, which indeed it is, then objects of type animal can be replaced with objects of type lion without altering the desired behavior of the program. So that means I can rewrite this entire thing as lion is equal to lion and then pass in lion over here. If I do that and run the code, it should print out roar 2 times, and that's what it does. This is list cost substitution. I've substituted lion instead of animal because lion extends animal. And I've done all of that without affecting the correctness of the program both the times it's printing roar. Now you might ask, isn't this how inheritance works? So if there is a subclass and a superclass, they can be interchangeable, right? So what's new in list cost substitution? List cost substitution tells us more about how inheritance should be used to maintain the correctness of programs and ensure the substitutability of objects. This means that simply inheriting from a superclass doesn't automatically ensure that a code is following the list cost substitution principle. You also need to make sure that subclass doesn't violate the contracts established by the superclass. And we need to make sure that it doesn't alter the behavior in unexpected ways when substituting objects. Let's say we have code like this. We have class animal with run function defined inside of it, and then class lion is extending that animal class. And inside of that we have void run. First we are calling the parent class super.run, and then we are printing the lion is roaring while running. And then in the main function I've created animal is equal to lion animal.run. When I try to run this, what do you think it will print? It's going to print the animal is running, the lion is roaring while running. Here in this code, we are violating the list cost substitution principle. And that's because if we substitute a lion object instead of an animal object, it leads to unexpected behavior. So if I pass an animal over here and then run our code, we have the animal is running over here. However, if we have lion, it says the animal is running along with the lion is roaring while running. So it means that if I replace lion with animal or animal with lion, it's going to give me two different outputs. That means it's not following list cost substitution. So what are the benefits of using list cost substitution principle? When we use list cost substitution principle, each class can be treated as a standalone module, which means it can be developed and tested independently of other classes. This promotes modularity, meaning it allows us to break down a complex system into smaller and more manageable parts. And when we follow list cost substitution, we can also be sure that every class in the group behaves consistently. This means that each class will implement the same set of methods and have the same behavior as the parent class. This consistency can help reduce the chances of catching bugs and unexpected behavior, and therefore we are improving the overall code quality because that's the point of all of this, reducing bugs and catching bugs faster. Now that we have understood list cost substitution principle, let's get into the I of solid principle, which is interface segregation. Interface segregation states that clients should not be forced to depend upon interfaces that they do not use. Interface segregation principle, or ISP, basically emphasizes the importance of keeping interfaces slim and relevant to the clients that implement them. This is why it might feel very similar to the single responsibility principle. Each class or interface that we create serves a single purpose in this principle too. So let's take a coding example. Let's say we have a big code like this. We have our interface worker, which has two methods, work and eat. And then we have two classes, developer and waiter, implementing this worker interface. So we have work, developer is working, eat, developer is eating. Then we have waiter, which implements worker again. And then again we have work, where we are printing waiter is working, and eat, where waiter is eating. And in the main function, we are just calling all of the functions for each of the two classes. Now this code might seem fine, but we have a problem here. Not all workers have the same capabilities. Some workers, like a developer, only need to work, while others, like a waiter, only need to eat. Let's assume that they have a break to eat, okay? So this setup violates the interface segregation principle because this forces all workers to implement both methods even if they're not relevant to their role. The developer is only working, they're not eating, so this should not even exist for them. But if we don't have eat, it's going to throw us an error. And similarly in waiter, they should not have work, they're just eating right now. Now this code is a violation of interface segregation principle, and that's because our clients, the developer and waiter, are forced to depend upon interfaces they do not use. Definitely, developer wants one function work and waiter wants one function eat. We don't have to force both of the methods on both of the classes. Our clients should not be forced to depend upon the interfaces. That's the definition, and that's what we are doing right now, and that's why this is a violation. Now, how do I fix this? So to fix this, we can segregate the worker interface into more specific interfaces, each representing a different role, and have the classes only implement the particular interface that's relevant to them. So for example, instead of having the eat method in the worker interface, I can remove it and create another interface. So we have abstract interface class. And this is going to be, let's say, eater, and then we pass in the eat method inside of this. All the interface methods related to eater are going to go inside of it. Now what I can do is developer implements worker and the error goes away. You see, we only had to implement work method, and the waiter should implement eater because they're right now just eating. And this way we have fixed our code. This follows list cost substitution principle. Now obviously in the main function we can remove developer.eat because developer doesn't eat anymore and waiter doesn't work anymore. And there we go. This follows our code, and if we run it, we should be seeing an output like this. Now you might ask, what if the waiter starts working? What can we do? Well, in that case, you can have worker implemented over here. A class can implement two classes. So now I can have my work function passed over here as well. And then I'll say waiter is working. So this might seem simple to follow, but when the code grows, it can get tough to follow this principle. So as a rule of thumb, whenever your implementations provide empty methods, it means that interface segregation principle is not followed. So earlier when I had worker having work and eat method, the eat had to be empty inside of developer or had to be completely removed. If that's a scenario you face in your code, that means you're not following list cost substitution principle. So what are the benefits of using interface segregation principle? As I said, interface segregation principle is very similar to single responsibility principle. Each interface should have their own responsibility, and that's why all the benefits mentioned in single responsibility principle are there for interface segregation principle. The D in solid principle stands for dependency inversion. Dependency inversion is the strategy of depending upon interfaces or abstract functions and classes rather than upon concrete functions and classes. So when components of a system have dependency on each other, we don't want to directly inject a component's dependency into another. Instead, we should use a level of abstraction between them. Let's use an analogy to understand this. Imagine you're building a house. A house is a high-level module because high-level modules contain the complex logic or the overarching functionality that end users interact with or benefit from directly. So the end users are going to directly interact with the high-level module. So the house is the high-level module and it depends on an electrical system, which is the low-level module. It is a low-level module because it is closer to the operational details and interacts with the hardware or performs specific tasks related to the hardware to provide some power to our house. So if you design your house to only work with a specific type of electrical system, let's say a particular brand of wiring or outlets, you're creating a direct dependency. You're locked into that choice. If in the future you want the electrical system to change, maybe because it becomes obsolete or expensive, or if you just want to use a different system for any reason, you'll have a hard time changing it without redesigning the entire house. And that's what dependency inversion is telling you. It's telling you that instead of designing your house to depend directly on a specific electrical system, you should design it to depend on an interface or an abstract representation of an electrical system. This way, any electrical system that fits this interface can be used, making it easy to switch systems without having to redesign your entire house. Let's see an example of this in terms of code. So I have a low level module called incandescent bulb with me. Here I have two functions, turn on and turn off. And it's just printing that incandescent bulb turned on or it is turned off. Then I have a high level module, room. And this high level module has a dependency on incandescent bulb directly. And in this we have two functions, switch light on, switch light off, where I'm just calling the turn on and turn off method of the incandescent bulb. So in this example, the high level module, room, is directly dependent on incandescent bulb, a lower level module. This violates dependency inversion principle because room is not flexible to the changes in the type of the bulb used. Maybe later on I want to use an LED bulb, not an incandescent bulb. Now, how can I fix this so that dependency inversion principle is followed? So to follow dependency inversion, we will have to introduce an interface for the bulb, and that interface is what the room high level module is going to depend on. So here we're going to have abstract interface class bulb, and in that we're going to have two functions, turn on and turn off. Now the incandescent bulb is going to implement this bulb, okay? And obviously don't forget to put override here, even though it doesn't give you any warnings now. Now in our high level module, instead of using incandescent bulb over here, we can use bulb. So we are not directly depending on the lower level module. We have introduced an interface through which we can interact with the lower level modules. And the bulb is going to do the same thing because bulb has those functions, turn on and turn off. So now room depends on the bulb interface, not on a specific type of bulb. This follows dependency inversion principle, making the room flexible to changes in the bulb type. We can switch from incandescent bulb to any other type of bulb, and therefore we have achieved decoupling between the high level module and the lower level module. Basically, our higher level module doesn't depend on the lower level module anymore. So the benefit of using that is that we are depending on abstraction again rather than concrete classes. So high level modules are not tied to lower level details. So this separation will allow developers to change the behavior of the system by modifying or replacing low level modules without affecting higher level module. For example, instead of using incandescent bulb, I want to use, let's say, LED bulb. So I can create the LED bulb class over here. Let's call it. Then we can say LED bulb turned on and LED bulb turned off. Now I can just replace this incandescent bulb with this LED bulb when we call the room class, and we don't have to change anything in this high level module. So if changes in lower level module is made, high level module is not affected, and therefore we are also following open or closed principle over here. So I hope this dependency inversion was clear to you. So that's all I wanted to cover in this video. I'll see you in the next video where we build a project using clean architecture where solid principles are thoroughly followed.